Hey, welcome back everybody for the last lecture of the tutorial part of ML4MS. So as I said before, unfortunately Gaussian couldn't come, and then luckily Aldo and Claudio jumped in and quickly prepared a lecture yesterday. So they'll give the lecture together and it'll be the same format. We do roughly 40 minutes and 40 minutes again. So it's a joint lecture, but Aldo will start.
Probably will be a bit shorter than the other lectures. And definitely will take a step back from... hello? Yeah. So we'll take a step back and go back to potential once again, last time, probably, for the introductory talks. And I'll explain to you, I'll try to go through the other, let's say, big broad class of machine learning algorithms that I use nowadays to fit force fields, that is basically Gaussian process regression. So in the first part, I'll cover what is even more a prerequisite towards Gaussian process, and that's Bayesian inference. And you probably haven't heard about it as much as other fitting paradigm, and then I'll go to Gaussian process regression. In the second part that Claudio will show more results and something more specific to learning force fields. But first of all, what are we trying to do? So you all know this slide and this graph. We've got length scale and time scale. On the bottom left, it's ab initio simulations, and this is like the landscape of material simulation. You know, building machine learning force field is essentially doing this implicit modeling of the electronic degrees of freedom by modeling directly the energy of the system with a classical expression. Okay, first thing, I actually want you, if you want to stop me, just raise your hand and maybe ask a question. Probably, you know, even just like simple questions, I'll be happy to answer just to make this more interactive. This is really the task that has been approached and tried over the last 100 years, maybe already, maybe not, 60 years. And traditionally has been done in a way, now it's done in a different way, but the setup is always the same. So you have a small simulation coming from a quantum Hamiltonian, typically DFT. And this is like, let's say, a snapshot of this simulation with an atom. Then you decide that the force, so the arrow on the center on that atom, the specific atom, does not depend on atoms that are outside of a given cutoff. And then you try to learn this function that gives you the force with the input space being the atoms within a cutoff. So in this case, m equals 2. We have got a 3 times m dimensional. Maybe you might remove refraction, rotations, translation, so it's -6 degrees of freedom. And typically m is 30 or 40, so it's a high-dimensional regression. The output is a force, typically modeled as the derivative of an energy that is not observed because it's a local energy. And this is really the standard setting that has been done since always, in which then you learn a local function. This is assumed, so that if you scale to really high, big systems, everything is linear and everything is fast. This was also done traditionally, and this was done choosing a simple parametric form, let's say that of a Lennard-Jones, in which you have 2 parameters, and by trial and error you would try to fix these parameters. This is fine in the case of the Lennard-Jones. It's simple enough. You can just plot the 2 and see whether you have a best fit. But when you have like something more complicated and more useful, like the Ian potential, you go to tens or hundreds, or I think you can go to 1,000 parameters if you go to ReaxFF of complicated materials. These are extremely useful, but it's a really hard job. And of course, once you manage to do it, it's rewarding because you can run simulations. But definitely, it would be great to have a more systematic approach to doing these things. And recently, or relatively recently, the articles, the PRLs are 2007, 2010, we have assisted to this new paradigm in which you have a very flexible functional form. It's not a parameter form in which you have to choose the particular interaction. And you have, let's say, a neural network, or also I'll talk about this in a bit, Gaussian processes to actually model the functional form. So this is a lot more flexible, it needs more data, but definitely you can automatize the process of trial and error that was done by hand beforehand. So actually I put new in quotes because actually the first article I could find is 1994 that use neural networks to learn a force field, and it says our long-term goal in applying neural networks is to demonstrate that they can be used to interpolate complex and expensive ab initio databases that describe interaction between atoms. So they really got it well already in 1994, and now we're finally doing it because of computational resources. So before going to what's a Gaussian process, I need to go briefly through what's Bayesian inference, because that's really the basis of it. And we start with a data set, of course, that's always the case, but differently from a standard model approach, we encode our model into a probability function, and that is a prior probability. So these are our belief on what the actual interaction should be before we see any data. So in the case of the standard Lennard-Jones, that would be a Lennard-Jones functional form, and then let's say a Gaussian distribution for the two parameters centered at 0. So that's really a probability for each candidate function before we see anything. Then we need to design a probability that gives the so-called likelihood. That's that basically tells you what is the probability of an observation once our model predicts, let's say we have a system of a given geometry, and our model predicts that the energy should be 2 electron volt, and then what is really the probability that the energy is 2 electron volt? That's really the intuition behind it. You need to design it, and typically this is a Gaussian around our prediction with some intrinsic noise. And then the last step, which you want to obtain if you do Bayesian inference, is the posterior, so the actual probability of your model after you have seen the data. And this can be done formally in closed form for any model and any prior probability by using Bayes' theorem that just tells you take the prior, multiply it times the likelihood, just normalize it, and then you obtain the posterior. And pictorially you can see on the left some random functions taken from a given prior. You see they're all different, and you don't really know which one is best. But after you see 2 data points, then you see a mean function and random samples that do pass through the data. So this is really the algorithmic, at least the thought process of Bayesian inference, and it kind of resembles also our own learning process, right? We have prior about the world, then we get data, and we update our prior into a posterior, and so on recursively. But if this is not something clear already, then, and if you're not used to think about fitting in probabilistic ways, it's actually useful. I think it's quite illuminating to rethink about something you all know, and it's least square fitting. In fact, this was discussed already, for instance, in the talk of Luca Ghiringhelli. So you have some model f of w with some parameters w. You want to optimize these parameters, and you write down your loss. There's a square error loss with some penalty that doesn't allow parameters to go huge with alpha in front of it. And you just minimize this. In fact, if you assume that your parameters are Gaussianly distributed around 0, that's P of W, and you assume a likelihood that's also Gaussian around your prediction, with sigma f as a noise, then it's simple to see that the product of the two and the log of the product of the two is proportional to the squared error loss. So whenever you minimize a squared error loss, that's typically done when you fit a neural network, you are actually taking the maximum, because it's a minus sign, the maximum of your posterior estimate, so your posterior distribution about the true parameters. That's, I think, quite interesting. And it kind of matches the two. Of course, this is not Bayesian, because you don't find the distribution, you just find the maximum of it. And the real Bayesian approach is to find the whole distribution, and that's really what you can do with Gaussian processes, and I'll talk about it in a bit. But first, let's also really discuss why is it useful to contextualize the learning into Bayesian terms. So this is again Bayes' theorem, prior, likelihood, and posterior. You can really divide the the approaches that I discussed before, so the traditional and the machine learning non-parametric or neural network approach into two broad classes by the prior information that they've got. So traditional approaches have really high prior information. They really specify the functional form, and they have got few parameters, or at least they really have to pass through some specific limits and asymptotes so that you have to impose by hand. And so for that reason, they are limited in their accuracy. If they find some data that's not compatible, they are not going to be able to feed it. But they can be interpreted, they are fast, and they tend to be more transferable. That is really key, because you do impose by hand the physics. You are able to do that. On the other hand, of course, machine learning approaches are great. You don't have to tune by hand the parameters, but you don't know what's really happening in it. And you should be careful when transferring it to new phases. And this was interesting in a talk by Nong on Monday, and she was saying that you might as well just do a neural network for a specific application, and on that you're sure that you're not, you don't really need to be transferable. But let's say, can we really bridge the gap between these two approaches? Because it would be great to be able to systematically build a potential that, so without the trial and error, but it's also simple to interpret and really transferable. So this, I will argue, can be done in different frameworks as well in neural networks, but Gaussian processes are really a powerful way of doing so. So what's a Gaussian process? After we talked about Bayesian inference, this is quite easy to understand, at least in a high-level way. So you just put a prior on your function that's not a given functional form, it's just a normal distribution. So you assume that your function is normally distributed around 0 with a given covariance given by k. So that's a GP. And k represents really the correlation between your function at two different inputs, x and x prime. Then if you use a likelihood that's also Gaussian, you can, in closed form, solve Bayes' theorem and calculate the posterior. And this, the posterior, let's say, the probability of every function given the data is again a Gaussian process, and the mean function can be written in closed form. And what's really interesting is that you can write also the variance. That's a measure of uncertainty of your prediction in closed form. And you can see in that graph, but we will investigate that better. Random samples are now taken. This is a Lennard-Jones fit, and random samples are just taken close to the true function. This is very flexible. You can prove that a Gaussian process is equivalent to a neural network, at least with some kernel function, is equivalent to a neural network with an infinite number of nodes, but only one hidden layer. It has a really nice way of predicting uncertainty. It's built into really the framework. And what's really key is that you can build your prior knowledge relatively easily, into the kernel function. At that point, you see, the only thing that you can play with is really the kernel in the prior, and you can really impose all the properties that you want, or that you know they're right about the function, about the energy, potential energy in the kernel. So before we go and talk about what specific kernels one can use, there is a really nice way of visualizing Gaussian processes, and this is an animation that Adam did yesterday. So if we have a prior of a Gaussian process prior with that particular kernel, so squared exponential with a length scale L, and we have a likelihood with noise parameter sigma, and that's basically the uncertainty we have got on the data. Then what's the posterior? This, and really this is a tool. Basically, you can see here that oops, sorry. Do 1 second. Okay, so this is, again, a Gaussian process fitted on one data point of a Lennard-Jones with a given length scale and a given noise. So you can see, okay, increasing data point will just change, of course, the posterior. I'm plotting the posterior. And you can see how basically also changing the length scale completely changes what you learn. If you have a very low length scale, then you just fit the data point and you don't extrapolate at all. If you have a very high length scale, then of course you are able to better extrapolate. And of course, if you have higher noise instead, you don't have confidence on the data, and so you are again not able to fit, or you need more data. I mean, if you want this can be put online. I think it's quite nice. Anyway, the important bit here is that the predicted variance blows up whenever you are far away from what you know, and this can be really important in validation and in trusting your algorithm outside of where you have data. This is really was discussed already by Michele before. So again, what's really key, as I showed you also in this animation, is all this length scale and the noise and the kernel is the prior information that you build in your algorithm, and that is encoded into the kernel and its hyperparameters. So what one should try to do is to include into this function everything we know for sure, and that's all the symmetries, translation, permutation, rotation, and that's the extra step, a controllable degree of how much you want to make it complex, because a Lennard-Jones is simple, and then it extrapolates well outside of what you have fitted. If you have a super complex neural network with 10 hidden layers, then you might give it a lot of data, but it might overfit the data. Then the idea here is that you can control the complexity by controlling the interaction order and having a classical, some kind of resembling of a classical many-body expansion. But this will be the topic of the second part. So yeah, please, if you have any question on this really introductory initial bit, yes. Yes, so basically you can think of it as maybe the animation is also helpful, I'll go to it later, but think about a multidimensional normal distribution with 10 dimensions. Okay, and then you have to think from, let's say you equally, no, let's go here for a second, because here you can also choose the samples. Here it is. So these are all random samples. And you can think of discretizing the space from 3 to 1.6 and have 10 data points that are randomly distributed with a Gaussian. So that's really the way of, and that's in fact how you sample anything and you plot anything. So if you think about the limit of discretization of this space with a Gaussian distribution multidimensional, that's really a Gaussian process. So you take a multidimensional with a given covariance that's a matrix. The matrix is n by n and the mean is n. Then you bring n to infinity and the matrix becomes a kernel that depends on x and x prime, and that's really the covariance of the multidimensional Gaussian distribution, and the mean is just a function that can go through the data. So it's really the limit of a normal in the infinite input case. But really you're only interested in discrete, you can just think about it as a normal distribution. Thanks. I think that is important. Other questions? Otherwise. Yeah. I mean, I can expect the initial part to be less prone to questions than the second part, which is more on the actual details.
Okay. Everything clear so far?
Okay.
So I guess then we don't have to take a break, right? Can we continue straight away? That way you go to lunch faster?
Yeah.
Yeah. That's a good incentive. Okay, then let's just continue.
Okay, cool.
Okay. Oh, fantastic. Hello, I am Claudio Zeni, and I will just continue this talk and hopefully not bore you too much. So let's keep going here. So, as Aldo said, the focal point of any Gaussian process regression framework is the kernel function. And we heard about in these days that we really need to encode all of the possible information we can into this kernel function in order to facilitate the learning process. If you have to learn every time that rotating an object doesn't change its nature, well, that's a hard task. So we want really to encode these symmetries into the kernel function. Especially, you should know them by heart right now. It's permutational invariance, translational invariance, and rotational invariance. And these can be encoded quite easily into the kernel. I will explain it in a bit. But another aspect of the kernel which is often not analyzed is its complexity, its interaction order. This is a concept that goes back to classical potentials. If you think of a Lennard-Jones again, it's a two-body potential because the energy is divided into atomic pair energies, and the energy of a pair only depends on the distance between two atoms. And the global energy is just the sum of all of these terms. A three-body potential like a Tersov improves this concept and goes to three bodies, so the energy now is decomposed into groups of three atoms, and the energy is a function of either the three distances between them or two distances and an angle, depending on the formulation. Also, kernel has the property, so you can formally define the order of a kernel, which then will create an order of the potential that results for using that kernel. So it's very important to keep in mind, and lower kernels will be simpler, but also more transferable, easier to train, and faster. Okay, so let's go a bit through the actual derivation of building a kernel. We start from a descriptor, because we have to transform this atomic environment, which can have many representations, into something that we can use in a kernel. So the most commonly used concept, which is also used in the SOAP kernel that I will present later on, is to put a Gaussian on every atom. You put a Gaussian function in the three-dimensional space on any atom, and if you sum them all, what you obtain is a scalar field in the 3D space. So at every point in space, you have a value which is based on how many atoms are around it, basically. And these Gaussians have a smearing, a standard deviation, which is sigma. Now, to create the simplest possible kernel you can have in this framework, you take two atomic representations of two environments, rho and rho prime. You just multiply them and take the integral over the space, the 3D space. And this is nothing but a two-body kernel, because you can demonstrate that everything depends only on the distances between atoms. Unfortunately, this kernel is not very useful because it's not rotational invariant. If you rotate one configuration with respect to the other, the integral will change. So what you can do is to impose symmetry. As you already heard about, you can impose symmetry by doing a rotation over an integral over the rotation group. Any kernel of any bodiness can be integrated through Haar integration and be transformed into a rotational invariant kernel. And what you do is you take your kernel and you integrate over the rotation space one configuration and the other which is always rotated. So you do this, yes. You do the integral between the configuration rho and the rotation of the configuration rho prime. This is applied to any kernel. Haar integration is tricky, can always be applied, but sometimes it can be very complex and sometimes almost impossible to do. So let's talk about SOAP kernel, which is one of the most commonly used kernels, and let's go through actually the derivation to understand what's going on here. Because I think this is very important didactically to understand when you actually start to use them. So we start again by representing the local atomic environment. As a neighbor density, it's the same thing as before, but we also put a cutoff function because we are making the locality assumption. Everything is important up to a cutoff, and we would like the descriptor to go to 0 smoothly for derivation purposes at the end of the cutoff. So we just plug in that cutoff function, which is a function of the distance from the central atom. We have our descriptor. We then realize that it's tricky to do the integral over the rotations, so what we can do is to expand this and represent on another basis, which is composed of spherical harmonics and radial functions. Spherical harmonics will take care of the angular part of the descriptor and the radial function of the radial parts. And we can write this as a sum over 3 indexes of a coefficient and the spherical harmonics functions, which you can see here. And I think you already saw yesterday in Filippo's tutorial exactly this GIF, which is very nice. We realize that if we take the power spectrum of this object, so if we take a sum over the M index of C star C, we obtain an object, this P tilde N and prime L, which actually encodes information about a three-body term. So you see that the index is N and prime L. N goes over the radial function. N prime also goes over the radial function, and L is an angular term. So this is a three-body descriptor of the environment. This is an array. We can then normalize it and obtain this final descriptor, which is Pi. The subkernel now is nothing but the scalar product of the descriptors between two environments, and then we raise to a power to basically improve the meta-embodiedness nature of this object. So this is the final kernel. You go through this derivation and you obtain this, and you can now use it in Gaussian process regression. I will just showcase here one of the most recent uses. This is a paper in which the speaker that should have been here, Gabor Chani, participated and came out just this December, where they built a potential for silicon, but not only for bulk silicon, but also for surfaces, defects, and amorphous phases all at once. So they took a huge DFT dataset. They subsampled from this huge dataset a number of training points which was appropriate, around 10,000, and they built a unique force field for all these silicon phases. And it's nice to show that they predict properties which are physical, very close to the DFT level. For example, heat capacity on the left, thermal expansion, the phonon spectrum, and other properties which are plotted here. And the nice thing is that this unique potential behaves very well, and it behaves on average better than any other potential designed specifically for silicon. And this was not technically designed specifically for silicon because it's a Gaussian process applied to the data that comes from silicon. So you can see that this tool is very powerful and can lead to very good uses in this case. Also, there are other ways to build kernels which are useful. Actually, there are many, almost infinite ways to build them. But now I will focus on one way, which is, I believe, simpler to visualize and also faster to, computationally faster because of its simplicity most of the time. So if you imagine that you decide to impose a prior information on the nature of your kernel, so you decide that, okay, in this system, I only need the interactions up to 3-body, because I know that higher order interactions, or maybe I see, when I do the training, that higher order interactions are not that relevant, so might as well use a simpler kernel. Well, you can design these kernels quite easily. Instead of going through the hassle of integrating over all rotations, you can just use descriptors which are inherently rotational invariant. This is a very simple concept. So you can just design a 2-body kernel, which is automatically rotational invariant, by simply design, okay, my kernel is a Gaussian exponentiated difference of the radii between the atoms in the configuration 1 and the atoms in the configuration 2. You just sum over all of them, and this is already a 2-body kernel. This concept is very easy, and it's also very easy to expand. You go to a 3-body by taking, instead of couples of atoms, triplets of atoms. And you compare their distances and angles. You can then bring this to the many-body level, so infinite expansion, just by exponentiating a 3-body kernel, the distance based on the 3-body kernel. These very simple kernels are easy to construct, are inherently rotational, permutational, and translational invariant, and they're very fast to compute. And they are equivalent to the ones obtained through higher integration in the O3 group. For example, here you can see this is an toy example just to show that actually the dotted and the continuous line are the same. One is the higher integrated, the other is the one built on already invariant descriptors. So once you have this plethora of kernels you can choose from, well, which one is the right one for the job? This is actually an interesting question because you will always like to use the simplest kernel that actually satisfies your accuracy requirements. So in very simple systems, simple in the sense that they are easy to learn, it's better to use a simpler kernel. In crystalline nickel, on your left, we see that the two-body kernel in red reaches an accuracy, so the error is low, with very, very few training points. And this accuracy is reached by the many-body kernel, which is most complex, only, for example, at 1,000 data points, where the two-body reaches it at 50. So in this case, obviously, you want to use the two-body kernel to describe this system. Of course, the more complex the environment, the more complex the model has to be describe it. And in amorphous silicon, the two-body is not good enough, the three-body is not good enough, and you actually need many-body or higher-order body kernels to describe the environment. So you would like to have a systematic way to choose, basically. You can either train them all and look at the learning curves and decide, okay, I need this accuracy, so I want to use this kernel. But there is also a cleaner way, which is based on marginal likelihood of the model. So you express the marginal likelihood for your model as a product between, actually a sum because it's a logarithm, between a fitting value and a complexity value. The fitting is dependent only on the error you make on your training set, so the more inaccurate the model, the more important this term will be, and the complexity is a measure of complexity of your model. So if you just sum them up and you want to use the model which has the higher log marginal likelihood because of the minus sign. So you see, for example, again, we look at bulk nickel. In this case, the two-body kernel has a very high log marginal likelihood, and it's very comparable to the one of three-body, which means that it's the kernel you should use. If you, instead of using a bulk nickel, you still use nickel, but now it's a nanoparticle. Nanoparticles are tricky because it's all surface, they can be in very different morphologies. It's a much more complex system, even though the element is the same. And you see that the two-body kernel is not selected because the accuracy it has is much lower than the three-body, which is actually selected. And interestingly, the many-body kernel, which is always the universal approximator, it can go to arbitrary precision given infinite data points, is not selected because the accuracy, this is the higher order kernels are not selected because their complexity is not worth the price. The accuracy you get is not worth paying the price for the complexity of them. So now that I tried to convince you that simple models are actually good in most systems, let me tell you a bit more about how to speed them up. So if you have a low-order kernel, which implies a low-order potential, which you can visualize in your head as a fancy Lennard-Jones, which instead of adding two parameters, you can draw it by hand. Actually, the program draws it by hand for you. Well, if you have this system, then why are we using all of the data points for our prediction? If our Gaussian process implies a potential, why don't we just use the potential instead of summing every time over the database, the kernel, and then multiplying by the weights? Well, we can actually do that. We take our Gaussian process, and now let's say it's a two-body for visualization purposes. This Gaussian process assigns to every distance between two atoms an energy. That's what it does. Well, we can just save this energy value for a distance between 1 angstrom and 10, whatever is your cutoff, store it. Now you have a tabulated potential. It's a potential which is a table and tells you what's the energy of a bond given a distance. You throw away everything else. Now you have a potential which is tabulated and which computational cost does not depend on your training set. Now it's just a table, it's a lookup table. So this lookup table is very accurate actually. This is the error done with respect to the Gaussian process on your left. And you see that with a sufficient number of grid points, so of samples of this table, the error is basically zero. It's negligible. It's much less than the error that Gaussian process makes on the data, so you can forget about it. And the speed does not depend on the number of training points. So the Gaussian process has a cost which is linear with the number of training points. If you sparsify it, okay, it's better, but it's still linear in number of bases, whatever. Oh no, maybe that's not true. Let's forget about it. So the MFF is, its cost is constant, and this is a very nice thing because now we can run very long dynamics or dynamics on very large systems. As an example of an MFF, on the left we have a toy example. This is just copper. It's just to show you how it looks. This is learning the Lennard-Jones. Well, it learns it well, thank you. But the nice thing is we have the accuracy bar, which Aldo already told you what they are, which tell us that we have no data in this region, so we're not really sure about that. So if we want to improve the accuracy, we will need to sample data points which have those regions in them. To instead show different actual approach, an actual potential. In this case, this is amorphous silicon. The top is the radial term. The bottom is the angular term, or a slice of it actually, at the minimum of the radial term. And you can see that even though this is amorphous silicon, it is quite interesting that even though the dataset does not contain crystalline silicon, the minimum is predicted to be in crystalline silicon because the minimum of the potential for the distance is the bond distance of silicon, and the minimum for the radial term is actually the minimum of the diamond structure, which is very interesting. So the nice thing about these models is that simple that you can visualize them, and you can actually extract knowledge from the data that goes beyond the force field itself. So now you have a framework, and you actually have a very simple way to construct systematically force fields for the system you need. So you take an initial database of your system. It's either you download it from the internet because someone already did the DFT calculations for you, or you do them yourself, but you don't need many. You need a few hundred steps, or even less, depending on the system size. So you don't need to do the actual dynamics because that would defeat the purpose of building a machine learning force field. You choose the order of the interaction need, either by heuristics, by prior, or by marginal likelihood, let's say a three-body. You train the Gaussian process, and you tabulate it. Now you discard everything, and you have this tabulated potential you save, and you can use in a molecular dynamics simulation. We actually did all of this and put it into a Python package, which is called MFF. And if you're interested, just ask us, and we'll tell you about it. It basically allows to do everything I explained up to now. This is the snapshot of the MFF package. You can go it yourself, just ask us. Additionally, it is interesting that you could use the GP uncertainty to, on the fly, train the Gaussian process if you wander into a region of configurational space which you don't know. Just to show you one of the first application we did of this MFF, we took a set of nickel-90 nanoparticles with different morphologies, and we trained them using a very small, actually, training set, 1,000 configurations. And we built a three-body force field for that, and we tabulated it. And then we ran many simulations trying to melt this object and seeing how it behaves depending on the temperature. So we predicted, what was already a thing that was thought in the environment, basically, that this structure is solid below 600-700 Kelvin. It's liquid above 1,000, but it's actually a weird mix of solid and liquid, which is called a slush state, in which basically the object is a Rubik cube, which keeps changing some of the structures. And we did this by doing 60 million MD steps on in 5 days on 24 not even very good cores. The nice thing is that this was done with almost DFT accuracy. It was the error on force was on average 10% on DFT, which is quite good. It's what you consider to be chemical accuracy for the system. And with DFT, it would have taken 2,000 years, which is a 10 to the 6th speed factor you get from mapping the potential, which is very good and interesting if you need to do very large systems or small systems, but for a very long time. Okay, to sum up this combined talk between Aldo and me, I hope that we told you about the importance of governing the complexity of a model and of actually understanding what's going on, and the advantages of simple models in terms of clarity, so you can see what's going on, accuracy, efficiency, and actually, yeah, that's it. You have that lower order models are usually good enough for the requirements you have, so you don't have to go many body usually. And the advantage of low order models is that you can map them to further increase their computational speed and actually do dynamics which are very similar to classical molecular dynamics, because basically that's what you do. You use a tabulated potential, and that's what you can do with classical MD. Okay, that's it. I would like to thank a small bunch of people. First of all, Professor Alessandro De Vita, who recently passed away, and he was a great scientist, a great mind, and overall a great person, and we will be eternally thankful to him because of everything he's done. And then we will also try to thank Dr. Adam Fekete for the collaboration with the MFF package, the general collaboration, and also the animations, and Dr. Kevin Rossi for all the nanoparticle expertise he brings into the problem. Okay, that's it. That was a very short talk. I hope you understood it, and if you have any questions, this is the time. Thank you very much.
The cube on. Okay, we have the mic on here.
You say you have a you have a tabulated potential. You said.
Yes.
How fast these potentials are to evaluate when you are doing your molecular dynamics?
Well, the potential is a tabulated potential. You just use a spline to interpolate in the value you are. So I don't know how to give you a measure of speed, but it's simply a spline interpolation between points.
It doesn't get complicated if I add more atoms to the...
more atoms in which sense?
But for example, here you have your silicon, right? Or
yes. What, more atoms in the environment or more atomic species?
In my system, let's say instead of silicon, I have silicon germanium or...
Okay, the more atomic species you add, the more complex the model. And basically, this system holds up to 3 atomic species, maybe 4 if you push it. Because of course, when you have more atomic species, you have more combinations of bonds and triplets you have to describe. So your space becomes larger and you need more training points. But the system is the same, you just need to train instead of 1 part, 4 parts of it. But at the end, the computation efficiency is exactly the same.
Okay, and just, I got lost in your descriptor. You start with the Gaussians, and then you have an integration over
the rotations, you mean?
Rotation. That's the moment you define your descriptor, right? Just in that.
No, the descriptor is actually the top one, the row. That's the descriptor. That's a scalar field in the 3-dimensional space. That's the descriptor in this case, in this specific case. Then, and also in the SOAP case, the starting descriptor is the same. But then if you go to n-body kernels, the descriptor is different. You already take the quantity you are interested in. So for 2-body, the bond length. For 3-body, bond lengths and angles.
Okay, thanks.
Okay?
Thank you. So I actually have physics questions rather than machine learning questions. So for the nickel clusters, how do you cope with magnetism?
That's an interesting question. In this case, the DFT we started with had magnetism in it, so it was not fixed. So it was able to actually go on the fly. And basically, we ignored it. We completely ignored it. And this is all... if you want to say it fancily, we implicitly include it into the model.
But so you're assuming that it's ferromagnetic? Or
when we train, we do not make any assumption of magnetism.
Well, but depending... so you clearly go across the Curie temperature. So does it... if you're above the Curie temperature, then you should sample over multiple spin states. This is the stuff that Jörg Neugebauer is doing for iron. Now, nickel is easier because it's a soft magnetic material, but so you just run spin polarized DFT.
So it was
for the DFT
Kevin
part,
here.
Kevin.
Yeah. It was spin polarized. We sampled the manifold of different spin states, and we did check that the forces all in all are not changing too much depending on the spin state. As such, we trained all of them together, and therefore, yeah, we assume that the Boltzmann probability of having a given state will be the dominant descriptor of the force, and for this reason, we will sample different configurations that will assume a average force between the different spin states. Again, the forces were not too different all in all. That's why we give us the freedom to do this.
Thank you.
Thank you. Water.
Thanks. So you're using your potential to run a very long MD, and you told us that if you have a configuration that you have not done before, you are turning on the fly the Gaussian process.
No, that's what you can do. That's
what
not
you can do.
What we do.
Okay.
This is a, let's say, follow-up step.
Okay. So when you do that, if you have an error in your initial Gaussian process, when you calculate the new configuration, you will probably propagate this error. So is it possible that your molecular dynamics is wrong compared to the real DFT1, meaning that you are propagating errors with the same? Isn't it? Wouldn't be efficient to check with the real DFT calculation from time to time just to see that you are not straying too far from the real dynamic?
Definitely, that's what you will do when you actually want to. Well, that's one way to do it. What we did is one step below that. We checked that the system was accurate also at higher temperatures. So we checked against DFT dynamics at higher temperature, and the system was accurate there. We did not check on the fly, but we checked on the ensemble. But what you say is correct. Okay. One way to, which is actually, but that defeats the purpose of being very fast, because if you have to run a DFT calculation every X points.
Yeah, just from time to time.
Yes, but if you want to really go fast, you can not even allow that. But
and
you
if
can
you
use
have like a very large system, you can't do DFT.
Also that, yes. So what the next logical step is actually to use the predicted error to see where you are, if you can trust it. You have first to assess whether you can trust it or not, and then actually use it in this case.
Thanks.
Thank you. And my question revolves around these. When you look at the different symmetries within your model, you talk about like permutation invariance and rotational invariance. I'm just wondering if you also have to consider other symmetry operations, like if you do a mirror plane, or if you have to do an inversion.
Mirror plane is included in the rotational invariance because it's over O3.
All right.
It's already there. Because it's not SO3, it's O3, the group.
Okay.
Yeah.
Thank you.
Okay, any other questions? Good, I don't see any immediate ones. Again, our presenters will be here for the whole workshop, so you can always ask them at a coffee break. So let's thank our lecturers again.
Thank you.